Hey everyone, today we're going to do something kind of cool. We're going to step inside the mind of an engineer and solve a really interesting real-world puzzle. We're not just looking for an answer here, we're trying to understand how a whole system really works. So let's dive in.
So here's the big question we're tackling today. How much sunlight does it actually take to pump water up a hill? It sounds simple enough, but the answer is wrapped up in physics, a little bit of mechanics, and of course, the power of the sun itself. This is the mystery we're here to solve.
All right, so here's the setup. You've got a reservoir of water down here and a tank way up there, a full 20 feet higher. Our only tools for the job? A solar panel to catch some rays and a pump to do all the heavy lifting. Our job is to figure out how to put it all together to get that water moving uphill. Okay, so let's dig into this solar-powered puzzle. This isn't just about plugging numbers into a calculator. It's about building a picture, a model of a real physical system, one piece at a time, to see how it all connects. To solve something like this, an engineer has to think like a detective. Seriously, the very first thing you do, before you even think about a solution, is you gather all the clues. You collect every single known fact about the situation. So, let's start gathering those physical clues. What are the key pieces of information we absolutely need to know to crack this case? We need to understand our power source, the machine doing the work, and the challenges it's up against. Okay, first clue, our power source. It's called solar flux. Now that sounds technical, but all it really means is how much energy the sun is beaming down on our panel at any given time. Think of it as the raw fuel we have to work with. Next up, the machine doing all the work, the pump. Now, every pump has this thing called a pump curve. It's basically its performance review, its personality profile. And it tells you something you probably already know intuitively. The harder the pump has to work, the more pressure it has to create, the slower the water is going to flow. Totally makes sense, right? All right, here it is, the complete case file. All our clues, all our evidence, right here in one spot. We've got the solar flux, how efficient our panel and pump are, the height we need to climb, and some really important stats about the pump's limits and the friction from the pipe. These aren't just numbers, they are the rules of the game, the physical limits we have to play within. Okay, we've got our clues. Now what? Well, a detective has to organize their evidence, right? An engineer does the same thing, but they use the universal language of math and equations to make sense of it all. We're going to build our model in 3 quick steps. First, we'll figure out the pump's behavior. Then we'll model the pipe's resistance. And finally, we'll put it all together and make them balance out. So you remember that pump curve we talked about? We can actually describe it with a pretty simple linear equation. All it says is that as the water flow goes up, the pressure the pump can create goes down. It's a nice, predictable, straight-line trade-off. Now for the pipe. And this is a really important one. The pressure you lose to friction isn't a simple one-to-one thing. It actually increases with the square of the flow rate. So if you double the flow, you get 4 times the friction. This resistance can get out of hand really, really fast. And that brings us to the grand finale, the system balance equation. It's actually pretty simple when you think about it. The push from the pump has to be exactly equal to the push needed to lift the water up that hill plus the push needed to fight all that friction in the pipe. It all has to add up perfectly. Okay, there we have it. The model is built. We've turned the real world into a set of equations. Now for the fun part, solving for that panel size. See, because our model knows exactly how much water is flowing and exactly how hard the pump is pushing, we can figure out the exact amount of power it's using. And all of that power has to come from one place, our solar panel. That's our target. And bam, there's our number, 2.152 square meters. That's the size of the solar panel we need. You think we're done, right? Case closed. Well, not quite. Because see, a great engineer doesn't just stop with one answer. The real magic, the real understanding, comes when you start playing with the model and asking, what if? So let's ask that what if question. What if the hill changes? What happens to our flow rate and our required panel size if that tank is higher? Or what if it's lower? How does the whole system respond? So when you start playing with the height, you see 2 things happening at once, and they're kind of fighting each other. As the hill gets higher, the pump has to strain, right? So the water flow naturally slows down. But at the same time, you need more overall power to lift that water, even if it's moving slower. So the panel size has to go up. And this plot just lays it all out beautifully. Look at this. As the height goes up, see that blue line for the flow rate? It just steadily drops. But the red line, the panel area we need,
It starts to climb, and then it just skyrockets. It goes almost vertical as we get close to the pump's absolute limit. Right at that 60-foot mark, the flow just dies. It hits zero. It doesn't matter how huge your solar panel is. And that is why this kind of analysis is so critical. It shows you the limits of what's even possible.
So let's take a step back for a second. What did we just do? We didn't just solve a solar pump problem. We followed a playbook, a really powerful one that can be used for almost anything.
And here it is, the engineer's playbook. First, you define the problem. Then you gather all your facts, all your clues. You translate that system into a mathematical model. You solve it to get a specific answer. And then, and this is the most important part, you analyze that model to see the bigger picture. You ask, what if?
And that really gets to the heart of it. That number we found, the 2-point-something square meters, that was just an answer. The real prize, the real understanding, came from that plot that showed us how the whole system behaves under pressure. That's the goal.
So it makes you wonder, right? This whole detective's playbook, gathering clues, building models, asking what other big, messy puzzles could we understand better with this way of thinking? Things like climate change or economics. It's a powerful tool for making sense of a complex world. Thanks for joining me on this one.